Any questions for Harry? Well, let me just ask one thing about what do you mean about genuine?
You know, the sorts of things that you now get in the movies. I mean, ultimately, that's what you want. You want to be able to walk around the model. You want to be able to see it genuinely three-dimensionally. Right now, the sorts of things you have are not genuinely three-dimensional. These are very good. I mean, they're certainly better than anything that people were producing 10 years ago. So there's a genuine advance. And again, you can call this a pedagogical issue rather than a research issue. But coming to understand how a model works very clearly is part of my research at any rate, as much as trying to understand the text of Aristotle is my research. It's about understanding how these things work. So I don't have any problems with that. Then there are also questions of, things that you can actually discover by having a good visualization. Of course, then you have the question, are you discovering things that could not have been discovered in the original conception of the model because you're seeing it better than someone in the ancient world? I don't know what to say about that, except that that's an important fact about the models. So if by playing with Ptolemy's latitude theory, you can see how he might have conceived of it, you can see at least if he's incoherent where the incoherences are. Ptolemy's latitude theory is wrong in the Almagest.
And I guess the interactivity with the model is also part of this journey. It would be great to not only to see in a real 3D environment, but also to interact.
Yes.
So what you were doing with a click of a mouse before should be doable by internet.
Yeah. So I'm not very good with a mouse. No. With two very different types of mice and two computers, but unfortunately these spreadsheet things just don't work anymore.
So a basic idea of the model was that the Earth is in the center and the Mercury, for example, always has the same distance.
In the Eudoxus model, yes. In the Ptolemaic model, no. If you go back to, oops, wrong. Well, I thought of bringing a mouse. I did bring a mouse with me, and then I thought, nah, I'm not going to use it. It's crucial in the Ptolemaic model that you can see that if the Earth is, let's go in a little bit. There's the Earth. You can see that as I need to show more of the model, show all of it. Oops, and the path. Oops, I just erased the path. Okay. So you can see in the model that as, still not showing all of it. Is that showing all of it? No? That's showing. Oh, there we go. Okay. So you can see, oh, I see that you just can't see it. Where's that thing? Well, Yeah, I mean, Mars rides what's called an epicycle, and the epicycle will pull it away and towards the Earth. Okay, and it's a crucial feature of the Ptolemaic model. And one of the things you want to investigate that's hard to, I mean, it's not hard to investigate it, you can write a computer program, but I mean, it's easier to visualize it, is the relationship between various aspects of the model. There's the epicycle, it's red. That's why it's hard to see. If it were a little darker, maybe. Now you can see it. Okay, there you go. So the epicycle here pulls Mars towards the Earth. That creates this motion over here, which is it's the retrograde motion. And one of the crucial things in the Ptolemaic model is the relationship between the Earth, which is over here, and these 2 points. So this is the center of that circle that the epicycle is riding, the green circle there. And this is, let's find that point again, there it is. The second point out there is the center of the actual motion of the circle. And this is the crucial thing. So the question is, why does Ptolemy construct this model where originally this thing over here is somewhere out there, it's further away, and then he does a second approximation which pulls it in and creates this point out here which separates the center of the circle from the center of the motion. And it's a kind of recursive procedure. It's what's called a recursive procedure. Anyway, why does he do that? Well, some people today think that the principal reason is to determine, to alter the shape of that retrograde motion, to make it less, to make it smaller in certain places. So anyway, that you can visualize how that works by playing with, by altering, where is it? I'd have to move it around, but by altering oh, I see, it's not showing. Where is it? By altering, there we go. Oh, by altering the deferent to the Earth to deferent, by altering this figure here, because those two lines are equal. So if you make this smaller or larger, you can, and by eliminating the that you can see how that the retrograde motion is eliminated, is altered very quickly, and then you can see exactly how one might, in a qualitative way, see whether that is the reason why one would alter it. See at least what the effect is in a very clear way. So that's an example of the sort of thing. In the case of the moon, let's find the moon. Trying to find there we go. In the case of the moon, Ptolemy's model is actually kind of bizarre because the moon moves very far and very near the Earth. And that's one of the classic objections to the Ptolemaic theory, is that eclipses should have, and full moons should have dramatically different sizes. I mean, the moon should be about 50%, 60% larger when it's out here. Sorry, when it's here than when it's out there. Indeed, that's one of the things that Copernicus did that was pretty quickly accepted, was to modify that aspect of the model. But in the Eudoxian model, it's you don't have variation, and this is a reason that someone gave for rejecting Eudoxus. Whether that is the reason that people gave up on the Eudoxian models, I don't know, but it's a reason that someone gave, that Simplicius gives for rejecting that he gives that people reject, for people rejecting the model. Whether or not they actually did, that is something that's unknowable. Okay. But again, it's something that becomes very dramatic when you see it in motion, like this.
I have one question about the relationship of constructing this model to the text.
Yeah.
Aristotle you mentioned, or Ptolemy in this case. There was a view before where there is also the text of this sandbox, the Visual Cosmology sandbox at the beginning, where you show the text and the model.
Yeah.
Are they interacting as the one you showed?
Well,
there was interacting.
Yeah. That's a good question. Let me see if I can. One of the things about how we plan to present it is, let's go back to Aristotle, or Eudoxus, is to present it with the possibility of explanatory text on the side. And so if you go to the Aristotle page, I actually popped in the text of the metaphysics, and just for fun we popped in all the manuscript variations. There aren't that many manuscript variations, so you can choose your own text if you like. That's kind of fun. That's a very bad text that I just chose, but anyway. The question, I mean, for Ptolemy, the question of fit with the text is quite easy because Ptolemy is pretty clear and the diagrams are pretty clear. There are a few places where it gets a little dicey, again in the latitude theory. In the case of Eudoxus and Aristotle and Calippus, these are three people living in the 4th century BCE. Aristotle's text is just that text there. For Eudoxus, we have that text there, and what Simplicius says in a commentary on De Caelo. And for Calippus, you have even less. You just have a comment at the end of this discussion and a comment in Simplicius, and that's it. So any reconstruction of Calippus is purely imaginary. I mean, it's simply a matter of you're told you're supposed to add an extra sphere here and an extra sphere there. So that's pure imagination. So anyone who claims that this is the theory is just pretending to themselves. With Eudoxus, there are two proposals out there. There's the standard proposal that was first put forth by Ideler in 1830, and then the formal mathematics of it was basically done by Schiaparelli in the 1890s. It was published in Italian, then German translation came out, and that was pretty much accepted by everyone until Eudoxus, who proposed something else. The difference between the two models is what counts as a rotation. So in Schiaparelli, a rotation is relative of one sphere is relative to the sphere next above it. In Eudoxus, it can be relative to a sphere yet two spheres above it. So the rotation of the in this model, the rotation of the there are, let's say, 4 spheres for Mars. So the rotation of the 3rd and 4th sphere creates that curve, which is called a hippopede. And the rotation in Eudoxus of the 4th sphere is relative to the 3rd sphere, which is the ecliptic, rather than to the 3rd sphere. I find the models implausible, but as an interpretation of the text, because there are technical difficulties that result. My arguments have been that Simplicius is extremely good, and that if you remove from Simplicius's own comments, things that I think are deeply part of Simplicius's own comments, then what you get left is something that is probably detritus of a 4th century BCE text by a guy named Eudemus of Rhodes. So these are things that you can dispute about, but the point is that when you get the models visualized, then a lot of the issues, not all the issues are clarified, but at least you can say, for example, okay, one question is what's modeled. Well, whatever you have as what's modeled has to be something that accounts for the existence of this funny curve. But then if you ask, okay, what accounts for the curve? Traditionally, what people have said is what they're trying to model is retrograde motion. So Yavitz's model does retrograde motion much better. On the other hand, you could ask the question, Bowen and Goldstein, two scholars in America, have argued that the Greeks of the 4th century didn't know about retrograde motion. That strikes me as implausible. But even if they don't know about retrograde motion, it doesn't follow that they're trying to model it. And then you could ask, what other phenomena are they trying to model? And then you could say, okay, does this capture, for example, this was a proposal of mine. Does this capture, for example, a variation in the time between the planet is last seen in the evening and first seen in the morning? Now, that's something that we know that Greek astronomers were interested in looking at for fixed stars. So surely that would be a possibility, but anyone who claims to have knowledge here is being, again, self-deceptive. I think skepticism is generally a good thing when one is dealing with these issues. But again, what the models do is, what the visualizations do is they provide you with a greater variety of possibilities. So, for example, there's a curve of Calippus that you'll find in every standard history book on Greek astronomy up through Neugebauer. And using these visualizations, I was able to see that there are actually other ways of constructing, on the same principles, a completely different curve, and a curve that actually works better. So, I mean, that's the advantage of being able to play with these things, is that they show you things that you don't see otherwise.
Are there more questions before we move to the wine? That seems to be the case.
We move to wine?
So let's move to the wine. Thanks
Yeah.
again.
Thank you.